Kristen and I are going to help you practice with some mock exams. All right, where we are this week is we are looking at circuits, as I said, and so we've been talking last night and tonight about current, resistance, and power, and we're going to add some batteries in a little bit. We're jumping a little bit in there. We're still going to talk about power, believe me. There's going to be plenty of power questions here. All right, let's keep going. So today's ideas, what you're going to do is you're going to have expressions that relate current and voltage and resistance to the rate at which heat is produced, calculate current and power, calculate relationships between potential difference, current, resistance, and power dissipated in any part of the circuit, and single known current, potential difference, or resistance in a multi-loop current using Kirchhoff rules. Now, we're going to talk, I should have thrown the Kirchhoff rules slide in there, but we're going to talk about those. And let's just review that real quick. We have the loop rule and the junction rule. All right, now I'm going to tell you, and we're going to do them in about, we're going to do them a bunch in the next minute. But the loop rule tells us that if I go around any closed loop, the sum of the voltage gains and drops has to be 0. And basically the loop rule is a conservation of energy rule. All right, so we can see here's a battery, and here we're raising the potential. And I don't know how much that is, but in a minute, I think we're going to do a simulation with 12 volts. And so we've got a 12-volt battery, and we can see that the current is going to flow. We always say the conventional direction of current is opposite that of the flow of the electrons, is out of the positive terminal around through the wires, and we say the wires are ideal. There's no voltage drop across the wires. They're perfect. And then we get to our first resistor, and we're going to have a voltage drop across that resistor. That means that I'm going to lose energy, my current. But what I don't lose is current, because whatever current I have here and here and here as well. And so the loop rule says that for each, that when I cross each of these resistors, I'm going to have a voltage drop, and the sum of those drops has to equal the voltage gain over here so that the total is 0. So I've got a simulation for us to check out here. And this is the first one that I have. This is the series circuit simulation. Now, I want you to, let's take a minute and we'll look at this and try and orient yourself. Down here, we have the battery, and there's a little voltmeter across the battery, and that voltmeter is telling me that I've got a 12-volt gain. You can see here's an ammeter here, 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 and here. So there's ammeters everywhere throughout the circuit. 1, 2, 3, 4 ammeters. And then we have 1, 2, 3 resistors. So this is what we're trying to replicate, 3 resistors and a battery. All right. But what I love about the simulation is, first of all, we get the animation of the current, and we can actually play with this if we want to, and we'll see what happens. Now, so you can see here that I've got a voltage gain of 12 volts. Now, I'm just looking at this, and I'm realizing that when I built this simulator, I put these voltmeters on backwards. So my apologies. But that's live TV. So they should say minus 4 volts, each of them, but they say plus 4 volts, but that's just the way it happened. So imagine if they say minus. If I had them correctly, they would. And so we've got a voltage gain of 12 volts, and then we've got a voltage drop of 4, a voltage drop of 4, and a voltage drop of 4 across each of these resistors. And so those all add up to a minus 12, and so my voltage drop is 0. And so that shows us Kirchhoff's loop rule. So any place we have a loop of current, we can apply it and make sure that we can account for all the gains and drops in voltage. All right, the next thing that I want to look at is the is the junction rule. Now we're going to add the junction rule. We're going to keep looking at the loop rule, but we're going to add the junction rule. And so the junction rule says that the sum of all the currents going into, I'm going to zoom in a little bit here. All right, so first let's talk about a junction. Here's my junction right here. Here's a junction right here. And a junction is where I have a current splitting or coming together. And so what I've got here is I've got a current that is coming in this way. And that is, remember, current is measured in amperes, but let's talk about what that means. Amperes are coulombs per second. Coulombs are literally charges. Now, it takes a lot of electrons or a lot of positive charges to make a coulomb, but that we're literally counting things. So coulombs per second, charges per second moving into this junction means that the current coming out this way, this I1, the current coming out this way, I2, and the current coming out this way, I3, all have to add to the current going into the junction. Now that's Kirchhoff's junction rule, and that's an articulation of the law of conservation of charge. We can't create any new charges, and we can't make any disappear. So however many coulombs per second are flowing into the junction is going to dictate the total amount of coulombs per second flowing out of the junction, just as if it were an incompressible fluid like water. Water is often used as a metaphor for electric currents. So let's take a look at the simulation for this parallel circuit. I'm going to go ahead and pop that up here. I think I've got that. Well, I'm going to have to open it up. And so here it is, the parallel circuit. All right. Thank you, Falstead Simulator. I love these simulations. They are just so good. I'm going to try and drag this a little bit more to the center so I can see if I can get it a little bit bigger. It's kind of small. Nope, that was not good. Let's not do that. All right. So let's notice over here, we're trying to, again, replicate this circuit. So you can see over here, the circuit, we have a battery on the left and 3 resistors on the top in the parallel circuit. So let's go ahead and get back to that. And so over here, we have our battery, and I've given us a 12-volt battery and 6 amps coming up. We'll talk about that in a minute. And we have 3 6-ohm resistors here, here, and here. Okay. And so if we have 3 6-ohm resistors, and I'm going to use my formula, inverse resistance formula, to find out what the total resistance is, that's going to become 2. And so I've got a total resistance in my parallel branch of 2, which means 12 volts divided by 2 ohms is equal to 6 amperes. And so I've got 6 amperes here coming through the main branch of my circuit. And so the 6 amperes flow into this junction, and now look what happens. I've got some flowing this way, some flowing this way, straight across, and some flowing down. I love how the simulator, take a look how it shows the speed at which the my dots are moving here, representing a current, versus much slower here. And we would have to say a third as slow, because since each of these resistors is the same, the current is split up equally among the branches. Now that doesn't always happen. It doesn't happen in the problems we're going to do tonight, but it does happen sometimes. If the resistors are the same, we'll split the current 2 amps, 2 amps, 2 amps. So 6 amps is equal to 2 plus 2 plus 2. We can also look at Kirchhoff's loop rule here. All right. And I'm going to actually try and freeze this for a second. So we'll do a snip and sketch, which a little ambivalent about this particular product. It's what I got right now. All right, so so here we are. Let me grab something to write with. All right, that's what we need. Great. And so let's take a trip around this one of these loops. And so here we've got a 12-volt gain. So that's plus 12. And then I come around here. And now look, I have a 12-volt drop. And these I put in
Okay, it looks like we lost Roger. So I'm going to pick up where he left off. And we're going to look at some practice problems because I think he was just wrapping up talking about that junction rule and showing as we go around those loops what happens, right? So if we go around that loop, we only have one resistor. So the potential difference drop across that one resistor should be equal to the potential difference of the battery. Okay, we could do that for any one of those loops and it would be the same. So all of these resistors that are in parallel have that same potential difference. All right, so let's look at some actual problems here. The first one is we have a student that is provided with a 12-volt battery of negligible internal resistance, and then 4 resistors. They all have different resistances, 100, 30, 20, and 10 ohms, but we also have plenty of wire that also has negligible resistance. So you can connect it any way you want. How would you connect those components up to create a circuit that all of the components have some current going through it, but we have as small of possible current coming from that battery? So you can't short anything out and have no resistors and have resistors that have no current. Everything has to have current going through it, but we want the smallest amount of current possible. Okay. So take 1 second. How would you do those? Maybe sketch out what the schematic of that would look like. And how do you know that that's what it needs to look like? So if we want small current from the battery, what do we want to be big, right? I can't change the potential difference of the battery. So if we look at Ohm's law, if I want a smallest amount of current possible, what do I want to do? I want to make sure that I have a very big resistance. So how can we connect our circuit to have a very high resistance? Well, when we're combining resistors in series, remember, we add them all up. So if I add all 4 of these resistors in series, no matter the order, it could be the 100 ohm first, or it could be the 10 ohm first. Doesn't matter what order they're in. If they're all in series, we could find what that equivalent resistance would be. If we add those all up, we get 100, 30, 40, 50, 160 ohms, which is a really big resistance, right? We could find what that current is from the battery because it's a 12-volt battery. And if we did 12 divided by that 160, we get 0.075 amps. Okay, small amount of current. what if we wanted to do it the other way, where we want as large as possible of a current going through it? What would we do? Well, if we want a big current coming from my battery, what do I want the resistance to be? Very small. And how do we connect a circuit up so that the resistance is very small? Well, that we do in parallel. So if we draw that circuit with those 4 resistors all in parallel, again, it doesn't matter what order we have those in. But if we now find our equivalent resistance, remember we combine those resistors in parallel by adding their inverses. So if we did and we found that equivalent resistance, then we get that it's only 5.2 ohms. So you can see what that difference is. If we combine those resistors in series, we get 160 ohms. But if we combine those same exact resistors in parallel, well, now it's only 5.2 ohms. Okay, so if we then again found the current, this time we get 2.3 amps. So much, much greater current when those are in parallel than when they are in series. Okay, what if we connect them like this, where we have that 12-volt battery, then we have the 100 ohm resistor here, we've got another branch with that 20 and 30 ohm resistor on it, and then the 10 ohm resistor. So first thing I want you to look at is when you look at this circuit, I want you to identify what parts of the circuit are in series and which parts of the circuit are in parallel. So do a quick glance at that. Tell me what's in series, what's in parallel. Okay, so what we want to know is really what I want you to do first is rank these for me. Like which one of these, so let's call this A, B, C, and D. Okay, so I want you to rank the current through the resistors from greatest to least. If any of them are equal, you're going to put an equal sign. All right, so tell me which one you say has the most current. Why? Why does the one you say that you rank first have the most current? And why does the one that you say is least have the least, right? So give me a ranking and a justification. I'm going to pause for just a second here for you. Okay, so I'm going to do this over here. So let's go back to which one of these are in series and which one of these are in parallel. If we look at B and C, well, they're on the same branch. So B and C are in series with each other. Okay. And then if we look at A, well, A, we have a junction before A. So if we were to write our loops here, well, let's do one loop. I could have current coming out of the battery this way, goes into the junction and comes out of the junction and back around like this. But we could have another one that comes out of the battery, goes again into this junction, but comes out this way and around and back to the battery. So we've got 2 loops here. So that means that A is in parallel with B and C. Okay. And then lastly, what do you notice about D? No matter which loop we take, both of those loops go through D. So D is in series with everything with the battery. So then D is in series with the battery and therefore everything. Okay, it doesn't matter if it's at the very end, right before we get back to the battery, if it's right after the battery, it's still in series with the battery. Okay, so anything that's going to be in series with the battery obviously is going to have the greatest amount of current. So ID is going to be the greatest. Okay, so let's look at then this junction and let's look at the current going down through B and C. We know since B and C are in series, they're going to be equal, right? But is the current going through B and C going to be greater than the current going through A, less than the current going through A, or equal to it? What would that depend on? Well, let's look at what the equivalent resistance is in each branch, because remember that potential difference is going to be the same because they're in parallel. But if we look at B and C, they have an equivalent resistance in this whole branch of 50 ohms, whereas the top branch has a resistance of 100 ohms. Okay. Well, the current's not going to equally split. We're not going to get half the current going through A and half the current going down through B and C. It's like when you're at the grocery store and you look to lane 1 and there's 3 people in line, and you look at lane 2 and there's only 1 person in line. Where are you going to go? You're going to go to lane 2. More current is going to go through your path of least resistance. So B and C are going to have equal currents, but they're going to be greater than the current that's going through A, because it's a greater resistance in that branch. Now let's see, how would we find that current going through D? Well, since it's in series with the battery, well, let's find what the current going through coming from the battery is. What do we need to know for that? I want to know the I through the battery. What do we need to do? All right. And Roger showed us the other night that diagram where you could make a table of the voltage, current, resistance, and power. And if that's easier for you, you can do that. I like to kind of draw everything right on my circuit. So that's kind of what I am going to do here. So if I find that total resistance, well, I know that these are in parallel. The 100 ohm is in parallel with the 20 and the 30. So if we combine that 20 and 30 and we get our 50, that's in parallel with our 100. So if we wanted to find that resistance, we'd have 1 over 100 plus 1 over 50. And if we do that, then we get that that's 33.3 ohms. But then these are in series with D. So then we have to add on D's resistance of 10 and get an equivalent resistance of 43.3. So I'm going to write that by the battery, 43.3 ohms. Okay. And then again, if we know 2 things at any one point, we can always find the third, right? We've got Ohm's law. So we can always, if we know either the potential difference in the current someplace, we can find the resistance, or if I know the resistance in the current, anytime you know 2 things, you can find the third, which is kind of why either doing this table is good, because if you've got 2 spots filled in your table, then you can see that you can do the third, or anywhere on my picture that I can see 2 things, I can find the third, right? So if I know the resistance and I know the potential difference, what can I find? I can find the current being supplied by the battery because it's the voltage divided by the resistance. All right, so if we plug in that 12 volts divided by our 43.3, we get 0.277 amps. Okay, so we've got 0.277 amps going into our junction here, but that's going to split, not equally, right? If we have double the resistance in the top, that should be getting half the current, right? But we get back to this junction and it comes back out. So again, at this point, it's going to be 0.277. Remember, current in equals current out. Okay, if we go around, well, since D is in series with the battery, that means there's 0.277 amps going through D. Okay, well, again, if I know 2 things at one place, what can I always find? I can find a third. So if I know the resistance and I know, oops, this one's the resistance, and I know the current, then I can find the potential difference across D, right? Because potential difference is the current times the resistance. So if we do that, we get 2.8 volts. All right, why do we care about that? Well, I can start going around and filling everything in if I wanted to and find everything in these elements, right? Because I started with a potential difference of 12 volts for my battery. Well, if I've lost 2.8 volts across resistor D, what does that mean is left for the rest of the circuit? Well, 12 minus 2.8 is going to give us 9.2. And since top branch is in parallel with that middle branch, that means the top branch has 9.2 volts. And total between B and C, we have 9.2 volts. Right, so we can apply, and we're not going to find everything, but we could go then, and now that I know the voltage drop across A and I know the resistance is 100 ohms, I could find the current through A, right? And then we could find the current going into the bottom one. We won't spend all that time doing that, but we're using these loop rules and these junction rules in conjunction with each other to solve the current and the resistance and potential difference in different places. But the next thing I wanted to ask you, which is another kind of conceptual thing that we like to ask, is if the light bulb, let's say, what color haven't I used here? Yellow. Let's say that A goes out. All right, let's take A out of play. If light bulb A burns out, I want you to tell me what's going to happen to the brightness of light bulb B and the brightness of light bulb D. Okay, so if A goes out, does B, let's say brightness of B and D go up, down, or stay the same? So I want to give you another second here, and I want you to think about that. And how do you know? They may both do the same thing. They may both do something different. But if A goes out, what happens to the brightness of light bulb B if these were light bulbs, and D?
Kristen, I wanted to tell you that I got back.
I'm glad. And we're going to come back to Roger here in just a second. So here's how I want you to attack these kinds of problems. When you're being asked to make predictions about things, when one thing goes out, and we're looking at, like, if these are light bulbs and we're looking at brightness, well, what does that relate to? It relates to power. But what I want you to look at is, how is your circuit changing? Are things going from series to parallel, or to parallel now to series? And how does that affect your total resistance and therefore the current, right? Because my resistor B is still going to have 12 ohms of resistance, and D is still going to have 10 ohms of resistance. I'm not changing the resistance through those resistors. So let's use one of those let's look at one of those power equations that doesn't have both current and potential difference, because both of those are going to be changing. But if I look at, say, I squared times R, well, of resistor B and D, R's aren't going to change. So what we want to look at is what's going to happen to the current. And really where we know that is what's happening to our circuit. So if I take A out of play, what does that now do to my circuit? Well, that gets rid of our blue loop, right? So now all we have is the green loop. And so now I go from a parallel circuit to a series circuit. So that's the first thing I would want to write, that we're changing from a parallel to a series circuit. And what does that do to our total resistance, guys? That means my total resistance, or my equivalent resistance, is going to increase. And if my equivalent resistance increases, what's going to happen to the current being delivered by the battery? That means my current is going to decrease. That total current coming from the battery is going to decrease. So let's look at D. That's kind of the easiest thing to look at first, because I know that D is in series with the battery. So if the current from the battery goes down, what's going to happen to the current through resistor D? It's also going to decrease. So if the current through resistor D decreases, then D is going to get dimmer. The brightness will decrease. Why? Because it has less current going through it for that same resistance. But let's look at B. What's going to happen to the brightness of B? Because our total current is now decreased, but what happens? We don't have this junction anymore. So there's no current going into that other resistor. Now all of the current from the battery is going through resistor B. So the current through B now is going to have to go up, because it doesn't have to share anymore with resistor A, right? So B now gets brighter, since it's now in series. And the current will increase through resistor B. Okay, so these are some predictions that are really good to be able to do, is if one thing goes out, what happens to the other, and be able to explain why. Okay, So we could find the total power, and there's lots of different ways we could do that because we know what the total current is from the battery. We know what the potential difference is from the battery, know what the resistance is with the battery. So we could use P equals I times V, we could do I squared R, you could use any of those power equations to find it. Okay, and then what about if the current remains constant? How long will it take to provide a total of 10 kilojoules of electrical energy to the circuit? All right, so we've got energy and we've got how long. Well, what's how long a measurement of? Time. So this still goes back to power because power, remember, no matter we're talking about mechanical power, electrical power, power is the amount of energy per time. So once we know our power from the first part, whether we say that that's I times V, and we want 10 kilojoules, which is 1,000 joules, or 10,000, I mean, then we can solve for our time because we know the power. I worked it out earlier and it's 3.32 watts. So we could find what that time is. We won't waste the time on doing the math. Okay, and then lastly, let's look at this last ranking here that I'll try to get through quickly so we can get back to Roger for a little bit. We've got this configuration of a circuit here where we've got our battery. We've got an amp meter here in series with the battery. And then we got a bunch of resistors and we've got 2 switches. And then we've got all these different possibilities of things that we could do over on the right here. I could leave switch 1 open and switch 2 open, which was what A is doing. So just like you see in the picture, I could close switch 1 and leave switch 2 open, right? We're going to change that circuit when we close those switches. So we want to be able to rank the amp meter readings for these 4 configurations. Okay, so what I want you to think about is, well, if we want to rank them from greatest, well, how do we know we have the greatest amount of current that's coming through the amp meter? Well, since the amp meter is in series with the battery, a big battery current is going to correspond to a small resistance. So we want to look at these and kind of find what would the equivalent resistance be for each case. All right, so if we look at A, and A is open, open. So just like the picture. Well, if we do our loop rule and go around the circuit, I start at the battery, we go here. Well, if switch 1 is open, we get to this junction. We don't have anywhere to go down there, right? Switch 1 is open. So we only can go through these 2 resistors that are in series. So let's just call this R and this R. So we got 2 R's so far. I keep going, I go around. Well, switch 2 is also open, so I can't go left. I can only go up. Okay, and I go around. I've got another 1, 2 still in series. So now I've got a total of 4R of resistance. All right, let's look at B. Erase these lines here. So B, we've got 1 open, 2 closed. So now we're going to close switch 2. What does that change? Well, as we go around, it didn't change anything in the beginning. I'm starting with 2R. Okay. We're going to go around and around and around. Well, I get to this junction. Now I got 2 choices. I can go up through this resistor or down through this resistor. So I've got those 2 resistors in parallel. Since there's the same resistance, then total, they're going to give me R over 2 or half an R. But I get here and then I'm in series again with this one. So that series one will give me 3 and now I've got a half. So now really I've got 3.5 R. You guys following me? Okay, let's look at if we have S1 closed, but S2 open. So now we're closing S1. And this is something, I don't know if we've talked about this yet or not, but if I have this closed, do we have any resistors in this portion of the circuit? No. So when I have switch 1 closed and the current gets to this junction, it's going to create what we call a short circuit, right? There is no resistance in that bottom wire. If there is nobody in lane 1 in your grocery store and there is even 1 person in all the other lines, will anybody go to those other ones? No, it's just short circuit. So all of the current will go down here. None of the current will go through those resistors. So I got 0 resistance, 0 resistance, 0 resistance. I get to 2. Again, I could go up here or down here, which gives me only half an R of resistance. And then I get to here plus 1. So for C, if I had just the 1.5 for my resistance. And then if we do the last one, closed, closed. Oh, switch one was open, so it couldn't go down through the bottom. Oops, this one should be just 2R. Sorry, guys. And then D, if they're both closed, again, we got a short circuit. So as we go around, I got nothing, 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 nothing. Now I get here and switch 2 is closed. So now we get to have just that 1.5R. Okay, so which one of those would have the greatest resistance? That would be D. So this would be first, and then C. Really, we're just going in reverse order. Okay, so looking at that equivalent resistance to find what your total current will be. Okay. Sorry, Roger, I'm so glad you're back. And we're gonna throw it back to you to wrap it up tonight.
All right, well, thanks for courage under fire there. Sorry that happened. I think it's because the computer heard me. I made a snipe about a Microsoft product and it just said, oh yeah, okay. Maybe that's what happened. All right, let's go ahead and move on. I've got a really good problem to finish out with you guys for tonight. This is a fun problem, not a problem that you're necessarily ever going to see on an AP exam. This didn't come from an AP exam, but I want you to take a look at it. It says draw an electric circuit that is consistent with the values of this chart and label the resistors. Okay, so let's take a look at this. So consistent with the values of this chart. Let's look at this chart. This is the voltage drop, current, and resistance chart. And we can see that we've got every resistor, and then we've got the battery. And they also give us the current through the battery, which is pretty useful. Now, I just want you to look at this for a minute and see, do you see any patterns? What might mean, how could we start? So I'll shut up for a minute. Well, I think we can all agree that there's one battery. And so I think that's a good place to start. So let's go ahead and start with the battery. And so here's my battery. And I'm told that my battery has a voltage gain. The EMF is 64 volts. Okay. And so we'll start there. Now, we know that the battery also has 12 amps of current. Okay. So we get that. So let's go ahead and we can actually put a little check mark there. We got those guys. Now what's next? Well, let's look. What is something that's obvious? Let's talk about the current first. Do we notice anything about the current? Well, we've got the 12 here, and we've got a 12 here and a 12 here. And I think a lot of you probably remember the loop rule we just talked about, where the current going into a junction has to equal the current coming out of the junction. If I've got 12 amps, I can't have a junction because there's no place for the current to go. Well, what does that mean? It means that these two resistors, R4 and R7, have to be in series with the battery and in parallel with no other resistors. So that doesn't prescribe exactly where they could go. So I could put this one, I could put one here, and I could put one here. I could put R4 here and R7 here. Or I could do it another way. I could put R4 here. Here I could put R7, and here I could put R4. That, for this problem, wouldn't make a difference. All right, so I can do that. And the reason I can do that, once again, is because these have to be in, they can't be in parallel because the current can't be reduced. And so once again, let's go ahead and say that we've got 12 amps of current through each one of these. There's my 12 amps. And for each of these guys, let's see, what did we have also? The resistance is 1 ohm and 2 ohms. And that'll be important later. All right, good. So let's go ahead and do that. Now I'm going to take these guys kind of out of the list just lightly. We'll erase this in a minute, but I want to be able to see what I can focus on. Let's look at what's left. So we can see what's left here. And let's talk about the junction rule again. Now, what did the junction rule tell us? Well, it told us that when we have a junction, the sum of the current going into the junction has to equal the sum of the current coming out of the junction. Well, if I've got 12 amps speeding along in this direction, and then I've got 5 and 5 and 2, that's a hint that these three, since they add to 12, they could be in parallel. That would work. That would satisfy the junction rule. So then let's ask, well, what is the potential drop across resistors in parallel? And we said it for a couple nights. When resistors are in when branches are in parallel, they have the same voltage drop. And so there's overwhelming evidence that these three resistors must be in parallel: R1, R2, and R3. And the resistors are, let's see, R1 is going to be 4 ohms. R2 is 10 ohms. And R3 is 4 ohms. Now, it does not matter for this problem in which order I put these. They are interchangeable for the way this problem is written. And notice they have the same voltage drop. Okay, good. So now we're going to come back together. Here's a junction. I can put the junction kind of like that, although that could confuse people. So I don't want to do that. All right, let's go ahead and keep going on that. Now, so now let's look at what's left. We got these guys handled. What's left are these two. Now look at this. They have the same voltage drop, which suggests they might be in parallel. And the sum of their currents sum to 12. Well, that's the overwhelming evidence right there. And so we're going to draw these two. We're going to have R5 out here, and that is 2 ohms. And we're going to have R6, and that is 1 ohm. And so that comes back to here. And then to go back and just, if you wanted to, it would be really easy to double check and go back and say, okay, well, what about the voltage drop? Let's look at the loop rule. Well, the voltage drop says the sum of all the voltage gains and drops around a closed loop has to be 0. So here I have a plus 64. There's the plus 64. All right, now I have a voltage drop of IR 12 amps times 2 ohms. That's minus 24 volts. Okay, now I have a voltage drop, and the voltage drop across this one we know is 20 volts. All right, and so that's a minus 20 volts because all of these resistors have a drop of 20 volts. And then here I have a drop of 8 volts. So as I go around the loop, gain 64 minus 24 minus 20 minus 8. And now here we're going to have another voltage drop across R7 of 12 volts minus 12. And if you add that up, 24, 20, 44, 52, and 64, that's the loop rule. And so with that, we're going to close it out. I love this problem because it forces you to kind of reverse engineer some of the ideas that we've been talking about. So you might want to rewind that, pause it, take a screenshot of it, try it yourself. It's a great problem. All right, I can't let up on the magic square of electrostatics, ladies and gentlemen. When you're studying this, don't forget your force, electric field, energy, and voltage. This is so useful. Newtons per coulomb. We have joules and joules per coulomb. Go back and fill out your magic square. It'll help you, I hope, on the test. So great you came tonight. Thank you for coming. We had a great time. Tomorrow night, as I said, we're going to put the capacitors in, maybe half a lesson early. Kristen, is your equipment working fine?
Yeah, I'm still here, Roger.
Okay, great. Well, again, sorry about the equipment failure. Thanks for taking over so abruptly, quickly there. Appreciate that. And can't wait to see you tomorrow night. Have a great night and study hard.